For joining us today for the California Drought and Climate Outlook Webinar. My name is Julie Klansky, and I work for this part of the CNAP program at Scripps Institution of Oceanography. And this webinar is brought to you by NIDIS, and I'm filling in for Amanda Sheffield, who is the California Nevada DEWS coordinator. And so for the webinar today, I will be giving a drought and climate, both the update and outlook, so talking about current conditions and then also what we potentially see or think might be coming. And then after me, Adrian Borsa from Scripps Institution of Oceanography will be talking about how we can use GPS sensors to understand water storage in the Sierra Nevadas and what that means for water availability. And after that, the third presenter will be Josh Stewartvent, who's now at NCAR, but was a student at University of Nevada, Reno, and we're talking about water supply forecasting skill with changing mountain snowpack. As we go through, if you have questions, please go ahead and put them in the chat. I will do my best to moderate them, and if there's time, we will answer the questions at the end of the presentation. Or also at the end of the webinar. This webinar is being recorded and will be up on a YouTube channel in a couple days, and we will send out an email to let folks know when it's available there. So with that, I will go ahead and get started. So here's the climate and drought outlook and update. So first, here's the drought status in California and Nevada. And as you can see, most of southern and parts of central California, there's no drought, but then the rest of the region has either abnormally dry conditions, which are these bright yellow DO, and then some drought ranging from D1 to D3. From most of Nevada and up all through the northern regions. So right now, about 61% of the region is in drought. And just at the start of the calendar year, or 1 year ago, about 98% of our region was not in drought. So that's been a quite substantial change from this year from prior year. So if we look at why, this image is showing the precipitation anomalies, so the percent of normal precipitation from this water year. So starting as of October 1st, 2019 through today, these are the precipitation anomalies which you're seeing. And there's this strong kind of north-south dipole where the southern parts of the region were much wetter, so above normal, in some cases 200% above normal, whereas the northern parts of the region were much, much drier. And before I continue, I put a link to where I got all this information on each of the slides. So if you want to dig deeper or see more, you can look at these or use these links to go to look at this in more detail. The Great Basin Dashboard has water year anomalies, calendar year, 30 days. And so there's a lot more information than I can present in these 15 minutes. So if you want to learn more, like I said, there's more information there. So then what about temperatures? And this year was more or less pretty average in terms of temperature. In terms of anomalies, it was 0 to 2 degrees throughout much of the region. Some area was a little bit cooler. So it was a relatively average year during this water year, so from October 1st to July 25th. However, and this last month, similarly, it's been a pretty average overall. It's been slightly warmer than the historical average, but overall, we haven't seen a really particularly warm year or necessarily a very cool year, which we see less and less frequently now. And so what this figure is showing is the Evaporated Drought Demand Index, or EDDI, and this is really looking at the landscape, the thirst of the atmosphere for water, and so how the landscape has dried. It does not take into account precipitation, but it takes in other variables like temperature, humidity, solar radiation, and winds. And so this is the 1 month EDDI. So this is looking at how anomalous this last month has been in terms of that landscape dry and the thirst of the atmosphere. And you can see some regions have popped out over this last month. So Northern California here, and on the southern border, eastern border of California. And then there are other regions that they're still abnormally kind of drier conditions, that the atmosphere is absorbing more water. There's greater thirst in southern Nevada region, and then kind of northern central California and into Nevada around the Tahoe, east of Tahoe. This is also true for, sorry, apologies, one of the problems with doing this from home. This is also true for the 3-month eddy. So this is looking over eddy for the past 3 months. So you can just see that there hasn't been such an intense thirst for the atmosphere, so intense drying, but it's been more widespread throughout the region. So now if we look into water supply, I'm going to be showing quite a few of these figures for different regions. They've been put together by Mike Dedinger. And what they're looking at is the reservoir level plus snowpack. And so this is an indication of water supply. And it's done throughout the water year. And so this was updated at the beginning of July. Obviously, there's no more snowpack, but the reservoir levels would have dipped down before then. So what you're looking at is over here, this image is showing the different reservoirs that are looked at for total water storage. That's this blue line is the average for that total storage, and the red line is the current condition as of July 1st. And then the gray is if you add snowpack on top of those reservoirs. And again, the gray is the normal, and the orange is the current water year, so starting October 1st, 2019. And what you can see was we started this water year with above storage in the reservoirs, and right now we had not sub-average snowpack overall, and so right now, as of July 1st, we're right about normal in terms of the reservoir storage. So one of the questions that Amanda asked about before she left on leave was what is groundwater? So I looked into this, and the Department of Water Resources has quite a few new tools to look at groundwater status. And there's a link down here below where you can see a whole bunch of different tools and interfaces. This is just one map, and this is the change from spring of 2018 to spring of 2019. I realize this is a year old, but this is the latest data I could find. There is a bit of a lag, I think, in getting this groundwater data, and that's something folks in our group are working on. And so you can see overall from this last year, there was a very minimal, most of the wells that they're measuring had no significant change, where there were some that increased, about 25% that increased, whereas, about 9% that decreased. And here you can see the different regions. So in Northern California, there were more that increased, whereas in the Southern Central Valley, there were a couple more that decreased. Now looking at Tahoe, this is a similar figure to what was shown before for the Sierra reservoirs, but this is just looking at Lake Tahoe itself. Here in the blue is the lake normal levels, and the cyan color is the one from this year, the water year 2020, and then lake storage plus snowpack is the orange line. And this year the lake was entered well above normal levels, and it is ending similar to where it started. And as I mentioned, Mike Dedinger is the one that puts these together, and he posts these on Twitter. So if you're interested, you can follow him on Twitter. And this is another one looking at the Colorado River Basin. This is showing, again, here are the reservoirs in the Colorado River that it's looking at, and then also Lake Powell. This is a bit more complicated because here are all the upstream reservoirs, so all these red dots, the normal. The snowpack in the Colorado River Basin is this white line. The dotted red is the upstream reservoirs plus the snowpack. And then what this green line is showing in this gray is Lake Powell versus plus all the upstream reservoirs. And one of the things here is because Powell is such a large reservoir, it kind of swamps out looking at, when you look at it on the same scale as these upstream reservoirs. And so you can see right here where we stand in terms of those upstream reservoirs are right about normal. And Lake Powell is pretty close to, plus the upstream reservoirs is pretty close to normal, just a bit below average for July. And again, Mike Dedinger posts these on Twitter if you are interested. Another great resource in looking at the Colorado and water supplies in California is put together by the Metropolitan Water District. And so in the upper Colorado River Basin, this year was 106% of normal for snowpack, and they're anticipating a 60% runoff forecast for the year. So looking at this, the question kind of is, what does this mean then for landscape and drought? We looked at the water supply drought, and overall in terms of water supply, we're doing okay. But the next question is, what about the landscape? And so this is put together by Dennis Ledemeyer at UCLA, and this is using two different hydrologic models that look at soil moisture, and these are based on percentiles. And the reason I'm showing two different models is it gives you a sense of kind of some of the variability. Soil moisture is something that is difficult to model, and when you measure it, it's only at one point, but how that point represents the broader scale can be difficult. And so models are often used, but no model is perfect. And so by showing two models, you can get a sense of kind of where the variability or differences between models show up. And so this is looking for one of the models, which is the NOAA-MP. This is part, for people familiar, of the National Water Model. This is the land surface model that's used. And you can see areas that it shows percentile-wise as being much wetter. So here in the Central Coast, and then also much of Southern California, and then the far Northern California coast up in Mendocino County. Whereas in Nevada, and on Nevada, in Western Nevada, you see a much drier area. The VIC model, which is a different hydrologic model, is showing some kind of the same patterns overall, but the percentiles are different. And so I think this is an indication that exactly how dry it is based on these models relative to historical, they're different, so that's not very clear, but the regions of drying is pretty consistent between the two. So this is earlier this year, I think it was in March, folks from the VEDRAG group, so it's the Vegetation Drought Response Index, presented on how they look at, or how they calculate drought and look at this. And so this is what the current VEDRAG index before California and Nevada. The gray are just out of season regions. But as you can see, what we're seeing, similar to the dipole and precipitation, we're seeing it show up in this VEDRAG, where there's moderate to severe and extreme drought kind of in eastern central Nevada and parts of Northern California as well. The last thing I wanted to mention in terms of the current conditions is the fire conditions. And so this is from the U.S. Forest Service Wild and Fire Assessment System. And so the color in the background is the fire risk. And you can see Nevada has a much higher fire risk generally overall, especially along the California-Nevada border into central Nevada. Whereas a lot of California right now, there's pretty moderate fire risk. In some areas, it's higher. Each of these orange dots represent an incident. I don't believe all of these are live incidents, but I couldn't find that entirely. Another great resource is this CAL FIRE reports, where it has information about all the incidents, particularly in California, and it does show incidents in Nevada. So if you're interested in getting more detail about these events, I would strongly suggest checking out this CAL FIRE link. So now I'm going to move on to the outlook, and this is going to look at both precipitation and temperature. And I know much of our region doesn't get much precipitation during the summer, but there is a slight part of our region that is impacted by the monsoon systems. And so for Southern Nevada and Eastern California, Southeastern California, I wanted to show that the 8 to 14 day outlook, so the next 2 weeks, week to 2 weeks, it's expected to be drier than normal. So an indication that there's not going to be a lot of monsoonal precipitation in the next couple of weeks. In terms of temperature, similarly, it's showing that in the next week to 2 weeks, it'll be a bit warmer in temperature, so above normal. And this is a new tool that's recently been developed. So there's different set of climate models that are run out for extended periods of time to look at extended range or 30-day temperature forecast. And this is looking at these different, here's when you combine all the models, and here's the individual models. And so what this is able to show you is kind of the uncertainty in some of these forecasts. If they were all showing the same general trends and general patterns, there'd be more certainty in this forecast. Whereas right now they're not, though the multi-model does show some cooling along the coast and warming throughout most of Nevada and the eastern portion of California. And I should have mentioned that the shading is in degrees. Just a couple more slides in terms of the outlook. And so this is looking at sea surface temperatures anomalies. And a couple of things to note. So we're really focused kind of on the Pacific basin, because that's what most largely impacts us, is you're seeing this warm blob off of Alaska. And this has developed quite a few years. Last year it developed, but it ended up dissipating largely before the start of the water year. But this large blob is becoming a more consistent feature, especially in the late summer into early fall. Another thing to note are these relatively cool temperatures along the equatorial Pacific. And that leads into the ENSO forecast. So this is looking at the ENSO status and the forecast going forward. And the gray bars is the probability of a neutral forecast versus a La Niña. And our region is impacted by El Niño and La Niña, especially the southern portion. And generally, La Niña is a bit drier. Historically, there's not a very, very wet year in terms of La Niñas. And so if you look going forward, there does later October, November, December, and January, the probability of a La Niña does exceed 50%. The other thing to note is the likelihood of having El Niño is very low. So just in summary, about 61% of the region is in drought between D1 and D3. In terms of the water year summary, there was a strong precipitation dipole. The north was dry and the south was wet. It was about average temperatures. The water supply in general, we're doing okay. We came into the season with decent water supply, even though Northern California was much drier, and Northern California and Northern Nevada were much drier. There has been significant landscape drying, so increased vegetation drought impacts and higher wildfire risk. In terms of the forecast, the monsoonal region is forecasted to be dry, though possibly with warmer temperatures. And that blob off of Alaska, the warm has returned, and a La Niña is possible for next year. So I will wrap up there to make sure we have time for our other presenters. And at the end, if there's questions, I'm happy to answer them. Okay. Joel, would you like to go ahead and change presenters, or do you want me to?
Yep, I'm on that. It's going to Adrian Borsa next.
Yes, thanks.
And okay, Adrian, you should be seeing a little pop-up on your screen to accept presenting. And once you've done that, we should see it.
Okay, I have to grant access. Can you try that again? Through a security.
Sure.
Let me try this.
Did that work?
Unfortunately, doesn't look like it. Still shows that it's on you. There we go. Okay, I've been made presenter. Thank you.
Yeah. Okay, we are seeing your screen. You are good to go.
Perfect. Okay. So as I was preparing this talk last night and into the wee hours, for some reason the talk kept encouraging me to go back to California Central Valley. So we're going to start there and then move on to the Sierra Nevada. What I mean by that, so California Central Valley, as you all know, located here in yellow, is one of the thirstiest areas of our state, and is also a place that provides certain agricultural products in incredibly high percentages to the rest of the country. So it matters quite a bit how much water the Central Valley is getting. So before talking about that, I'm actually right here in the middle of the screen is this red dot, and that's a GPS station. It's called Corcoran, or CRCN, and we're going to just focus in. We're going to take a look at this station to understand something about what's going on within the Central Valley itself. So Corcoran is on Route 43.
Adrian, sorry to interrupt. Can you put it in presenter mode? Down at the bottom, possibly. If not, it's not that big of a deal. We can see it just fine.
Are you able to see this?
Yeah,
is it in presenter?
that looks better. Thank you.
Okay, perfect. So the station Corcoran is indicated by this yellow arrow. It is completely nondescript. You never notice it driving by. That happens to be a GPS pillar mount, which looks like this, although this station is not Corcoran. So it is a geodetic quality antenna on top of a very stable mount. And the question we want to ask, so GPS of this quality is designed to measure daily Earth surface displacements at millimeter resolution. So what does Corcoran observe sitting here in the middle of California's Central Valley? Well, you already know something of this. There's been this sort of iconic photos like this one from 1977, not so far from Corcoran, showing these huge subsidence amounts in the middle of Central Valley. More recently, some of you may notice or recognize Michelle Sneed. She's been recreating these over more recent timeframes. And again, subsidence is continuing. So what these two photos have in common is the fact that they're in the middle of a region that's being pumped very heavily. So this is an arid part of the Central Valley. It's an overdraft from precipitation. Pumping groundwater is making up the difference. And pumping groundwater or over pumping groundwater collapses pore spaces at depth and causes incredibly large surface subsidence throughout the Central Valley, but particularly in this location. So if you look at what's happening actually at Corcoran, this image, the figure on the right is 2010 to actually till yesterday. I just pulled the data down, and we're looking at about 0 to 2 meters of vertical change on the vertical axis. It's not a surprise that then Corcoran is actually showing quite significant surface drop. What is surprising is the magnitude. You don't see these kinds of changes except maybe on outlet glaciers in Greenland and Antarctica. So this is one of the largest natural, well, it's human caused, but largest changes of Earth's surface pretty much anywhere. To give you a little context, so I'm showing you here on the left a snapshot of surface deformation for 2016. This is something my group has produced. You've seen this a lot. So Corcoran is right on this area of incredibly high subsidence. This is somewhere between sort of 20 and 30 centimeters per year. Right in the middle, this is north of Tulare Lake, and represents maybe the most subsidence, but there's subsidence occurring throughout the region as a result of pumping. The way that I interpret this, and this is not my hydrology and groundwater is not my area, but I see pretty much long-term subsidence that's here in this orange, punctuated by a few periods of uplift. So short periods, and we want to understand these better. For that, one nice way, so let's just take a look from drought.gov. Areas of California affected by drought, we see this latest, the 2012 to 2015-17 drought here as this really remarkable period of drought, but there have been droughts before and in fact after. And this is something that we just saw Julie show. So let's take this representation of drought and we put it on top of our Corcoran displacements, and what we see is that this upward motion really only occurs when there's no drought. In other words, there's plenty of surface water available as a precipitation directly to farmers, and then surface water being brought in by canal. So no pumping is needed locally, and there's a small recovery of aquifer. And then as soon as we get back into any kind of stress, these red and orange periods on the top, we see again a drop. Lest you think that this is just on cherry picking GPS stations, I took 4 GPS stations located in the middle of the Central Valley, and they all show similar, although different magnitude, trends here in the drought. And then recovery, and these recovery times, what happens afterwards is a little bit different. The station Tran, for instance, looks a little different than Corcoran, but the idea is the same. So the takeaway from this part is just groundwater pumping here continued in 2020 after these short breaks in 2017 and 2019. Subsidence rate right now is generally lower than in the 2012 to, let's say, 2015, but it's really 2016 drought. So keep in mind then large GPS displacements over aquifers indicate local groundwater withdrawal. Most GPS stations are not located over aquifers, and that's where we're getting to the second part of this talk. Before that, though, here's an article from April 16th from Science Magazine. And the point is this idea that, okay, so droughts have exposed California's thirst for groundwater. That most of us actually known this for a much longer time, but for a long time. And now the state hopes to refill its aquifers. And probably most of you are familiar with the Sigma Act. But really the question is, how do you refill these aquifers? I mean, what is the mechanism by which this might occur? So I'm showing Central Valley now in the context of the broader river basin that it's part of. So that's here in gray. That's the Sacramento-San Joaquin River Basin. And at least from the standpoint of the Central Valley, the main locations of water flowing into the valley are the Sierra Nevada to the east, and then the North Coast ranges here to the north. And if you look at just precipitation, so this is average precipitation, sure enough, the Central Valley, particularly the southern portion, is dry, even arid, but there's incredible precipitation around the valley itself, and all of this is sitting within this watershed. So the idea is we need to be able, as a society, to capture the water here, as the aquifers have done over history, and sustainably use the water that's available throughout the Central Valley. So state agencies want to refill the Central Valley. What are some relevant questions? And here I say, we'd like to know how much water is actually in the watershed at any given time. We'd like to know where it is. We also want to know, there might be water stored in the watershed, but will it become available to downstream users in the Central Valley, and over what time scales? If we put water in there this year, is it available immediately? Does it take a decade to come down, or a century? And then given available precipitation forecasts, can we better predict runoff And this is at all scales, even storm to storm. And this last bit is relevant to CW3's FIRO project, which is about managing reservoirs. Okay, so this is too much to tackle in one really short talk. So I'm just going to talk a little here about understanding how much water is in the watershed. My group and CW3 and other groups are interested in all these questions, but right now, this first one, just understanding where the water is the preliminary thing we need to know. Okay, so we are going to be looking at water storage and observing it through geodesy, which means essentially tracking the deformation of Earth's surface. How does this work? So now I'm showing you the same area, but this time instead of just the one coring station, which is right here in the middle, I'm showing you all the stations. All these are continuous GPS stations that are operating nonstop, gathering data and giving us a picture of how this Western US is deforming in space and time, is doing this at a daily level. So question we have is, what does displacement from a continuous GPS look like when it's not sitting over a pumped aquifer? So we've already seen the pumped aquifer, you drought, increased groundwater demand, and the surface subside, but that's actually very different than what's going on elsewhere. Okay, so for that, I'm taking another station. So this is Station Quinn. It's in the Yuba Feather watershed, and just as the vertical displacements here, it's roughly a couple centimeters of displacement. This is from 2008 to 2021. Again, this is all data I just pulled. And there's an annual periodicity in here, and then something that's longer period. And so you can already see it. We actually just break this raw data set down into its components. There's something that's seasonally varying, and this is something we expect. And then something that's non-seasonal, that's this gray. And then I gave you the smoothed time series in green. The question is really what causes the displacements that we see? Is it something local? Is it something far away? And for that, just a tiny bit of physics. Turns out that if you put a change in water storage, here represented by this water droplet, this could be in lakes or groundwater, soil moisture, snow, any change of that causes the earth underneath to deform. And it deforms elastically, I say like a mattress. So if you sit on it, if you put water on the earth, it subsides. If you take the water off, it rebounds, just like your mattress at home does. And the point is that if you put GPS on the surface, you can actually observe these changes. And you don't just have to be over the water storage location or the change location. You can be far away, or you can be in many places, and GPS will observe water storage changes pretty much anywhere. Just the issue is that any given station, you don't know exactly where that storage is coming from or where the change is. And so just keep that in mind for a second. So Quinn here is, if we interpret it this way, we say, okay, well, it seems that some of the motion is due to seasonal changes in water storage somewhere in its general location, 100, 200 kilometers from it. And then this long-term change, we can think of this as, okay, there's elastic rebound due to water deficit. So during the drought, that station was actually, the ground was lifting up. The weight was taken off of it. After this drought, this big California drought, we had a period of more water, and in fact, the extra water, the extra surplus of water pushed Earth's surface down, and so you get this subsidence. So now this idea of a GPS station out here in the mountains, it's actually showing uplift and subsidence based on water storage. So that's our observable. So these small vertical changes away from aquifers indicate water storage. And the key thing is that one station doesn't tell us a lot. We need an entire network of stations. But with that, it's possible to map these water storage changes over space and time. So that's the last short part of this talk. I'm showing you here, these are all the stations we were looking at before. In this case, they're just coded by vertical displacement relative to some long-term average. So in August 2011, most of the stations are showing some subsidence. And this is consistent with the fact that that was actually quite a wet period. Prior to the drought that occurred from 2012 to 2016. And so over time, as the drought progressed, these GPS stations all came up. So they went from blue, negative, to red, positive. They were uplifting, except for the stations that are sitting right down in the aquifer. So in the Central Valley, and then some aquifers down in the south. So on the far right, I'm showing you August 2015. I've removed the stations over the aquifers, and what's clear is that this represents maybe 3 centimeters, up to 3 centimeters of uplift relative to what it was back in 2011. From the standpoint of GPS, from the standpoint of Earth deformation, these are whopping signals. Doesn't seem like a lot, but they are. And the key thing, that the sort of hidden part, is we can take the displacements that are shown for any given time and then invert them to get the water storage at that moment. So here's an instantaneous picture of water storage. So displacements are plus or minus 2 centimeters here, mapped onto water storage changes in terms of equivalent water height of minus 30 to plus 30. And I can tell you in the Sierras, these storage changes get up to 60, 70 centimeters. So nearing a meter at the height of California's drought. So this time in August 2015, we see drought pretty much across the entire Western US. Texas is doing okay. The Mississippi River Basin, there's some drought here, and then something in New England. And we have these essentially on a daily timescale. And we can put together now, looking at this continental scale, we can look at watersheds. And what is that? So if we now take data like this, so snapshots of terrestrial water storage, and we just integrate in a particular area. So here's the California basin. This is HUC2 for those of you that know. And then just ask, okay, the seasonal component of water storage change from GPS in that basin, what does it look like? Here we have this curve on the bottom. This is consistent with what we know about California. Peak water storage in February, the lowest point sometime in sort of late July, August. Interestingly, so this is a battle between precipitation and evapotranspiration. So it's not just we get more rain in February and less rain in August, it's also how hot is it? How much water is being sucked out of the environment? And it turns out that it's huge. Evapotranspiration is about, really contributes to the shape of this curve as much as precipitation does. I point out Pacific Northwest, it's still on the West Coast, but Pacific Northwest has this long period here where the peak extends for a long time. In part, this is due to snow, and also it's due to evapotranspiration. Finally, I'm getting my last couple slides. The seasonal water storage is something we know pretty well. What's much more interesting is what's going on the interannual scale. So in this, I'm showing you here in gray, this is California water storage. Compared to all the other watersheds in the US, it has amazing variability, huge changes. So we're talking, I think, so this is 40 centimeter, 50 centimeter changes in water storage over this entire area. It's an immense amount of water. And what we see really clearly is the California drought showing up in this long-term, this water storage decline, and then the recovery. To date, I've not done the work to show what's going on right now, but from the GPS, it looks like the recovery got to about this point and then leveled off, and maybe it's dropping now. The final slide thing I want to show is that we're not only seeing these long-term changes, but in fact, individual storms are showing up as increases in water storage change. And one thing our data show is a storm brings a lot of water into the system, and it fairly quickly moves out through runoff and evapotranspiration. So it's really series of storms that make these long-term impacts in water storage change. So takeaway here, we're using GPS, we're using it in a different way to get at water storage change, which is very hard to do. It's something that's usually in models, but it's very rarely observed at these kind of temporal and spatial scales. So that's what I have. Thank you very much. And I'll pass it back to Julie and others.
Great, thanks, Adrian. That was super interesting. So thank you for sharing and giving that. We do have a couple questions for you. So while we pass controls to Joel. I don't know if we'll get to all the questions, but let's go ahead and start with one of them. One question is, do you think the groundwater recharge area basins that are being built are useful technique for slowing subsidence? And is there any data on this yet?
Good question. If I can find my, okay. So there is a groundwater recharge basin right in this area. And what I have not shown you is what happened in 2017 when this whole area actually came up because a lot of water was being put in there. It was a surplus year. I don't know the engineering issues. What we're working on right now is trying to understand recharge pathways in the subsurface from rivers. So the engineering part I can't say. I can say that it is clear that natural recharge is happening along river pathways, and the little tidbit here is that the groundwater basins that are currently specified here in yellow are not the basins that we're seeing. It's not where we're seeing recharge happening. So these basins are perhaps more political entities rather than they are natural ones. And it has implications for water management. If you're in one basin, you really want to know whether the recharge is happening in your basin or the one next door.
Interesting. Great. Thank you. Let's go ahead, and I know there's some more questions and we'll try to get them at the end. If there's time, let's go ahead and pass the controls to Josh. Thanks, Adrian.
Sure.
All right, here. Looks like you all can see my titles slide.
It looks good. Thank you.
Great. My name is Josh Sturdivant, and I'm presenting to you today on some work that I did at the University of Nevada, Reno with my advisor, Adrian Harpolt, but also others, including Mike Dettinger, who we've seen some other work from, Steph McAfee, and then Shay Rajagopal. And I'm going to talk to you a bit about specifically sort of this wintertime drought or snow drought, and what this low snowpack means for our ability to predict streamflow volumes on a seasonal basis. So in California and Nevada, much across the West, snow is obviously really important for delivering our water from our wetter winter months into those drier, hotter summer months. In addition to this, snow has been really important in that it provides a really convenient method for us to measure and then predict spring runoff. And in fact, this has been used for well over 100 years, the measurement of snow for the estimation of spring stream flow. It has an interesting history tied to Lake Tahoe and the UNR professor, Dr. James Church. And more or less, the same method is still widely used today by forecasters at the Natural Resource Conservation Service, but also in the state of California by the California Department of Water Resources, where they make both manual, but increasingly, of course, automated measurements of the snowpack as a way to estimate spring and summer runoff. But things, of course, are really changing. And we've seen long-term declines in snow water equivalents all across the Western US. And this has been shown to have implications for headwater basins for important aspects such as shifts in streamflow timing. If we look more regionally at California and Nevada, at a model data set, this is from Vic, from the CalAdapt website, and we look across a domain where historically there was a greater than 50% historical snow fraction relative to the total annual precip, and look at the change in what we're calling here snow drought defined as less than 25% of the historical mean peak SWE. We see that the frequency of these snow drought events is, of course, really going to increase double roughly in the first half of the 21st century, and then really take off as we move on. And so this raises important questions about what this change in the snowpack means for our ability to predict our spring and summer runoff. So as we see this suite of changes in our mountain snowpack, what does this mean for the long-range prediction of water supply, that is stream flow volume forecasts? And so our working hypothesis looks something like this, that basically as we move from a world that has more snow into one with less snow, that our forecast skill is going to generally decrease, but that there are going to likely be basin-specific attributes or regional attributes that are going to guide how individual basins respond to this change in snowpack, and thus our ability to predict spring and summer runoff from that snowmelt. And so today I'm going to walk you through two studies. The first is a historical analysis of water supply forecasts more broadly across the Western US, including some points in California and Nevada. And here we compared two of the most common operational hydrologic models from the Natural Resource Conservation Service and then also the river forecast centers to see how they performed relative to one another during low snow years. And then continuing this on into the future and leveraging VIC model simulations, seeing how Sierra Nevada headwater basins are projected to change using synthetic water supply forecasts, which I'll talk a little bit more about the methodology behind that. And then using this tool as a way to evaluate several strategies for mitigating the loss of forecast skill under declining snow. In this first study, we asked two primary research questions. The first simply is, are water supply forecasts degraded? That is, are they less skillful during below average snowpack? And what are the implications of this, if true, for different types of models, both empirical models and physical computer simulation models for future snow decline? To answer these questions, we used a model benchmarking approach where we compared these two models against one another to get a sense of their relative strengths and weaknesses. I'm going to give you a quick rundown on these two models to provide some background. The first is a very simple statistical water supply forecast model. This is what the NRCS uses, but is more or less the same flavor of what the California Department of Water Resources uses as well for their Bulletin 120 water supply forecasts. And the basic gist of this is that predictor variables from either automated or manual observation stations that become our forcing data are placed through a principal component analysis or some other statistical transformation, and then regressed against historical observed April through July. This window can change, but generally April through July stream flow volumes. And that looks something like this, where each one of these dots is a single site year, and this red line more or less becomes our forecast for future years. And to give a sense, the NRCS does this all across the Western US. And for this study, we recreated this process and issued retrospectively these forecasts at different lead times, but all predicting this April through July stream flow period for a set of about 34 years. And then compare this to our second model. The second model is the Sacramento Soil Moisture Accounting Model. It was developed by the National Weather Service in Sacramento. It is used widely by the river forecast centers, primarily for the short lead time flood forecasting, but they also do use it for this longer lead time stream flow volume or water supply forecasting that we're talking about here. And the details of this aren't too important, but it does consist of several submodels which partition precipitation into rain and snow, which then get fed to the SAC SMA model, which ultimately predicts this routed runoff or stream flow. And so we calibrated this model, and then we issued it across the same forecast lead times, predicting these same volumes over similar period of record. So this is more or less our workflow here, where we have our study basins, which consist of about 50 points across the Western US. We can see here the ones of interest probably to most of you all. And then in parallel, we're running our statistical model, that principal component regression, and SAC SMA, and then evaluating it using some common metric as a way to get a better understanding of relative model capabilities. And so if we look at some preliminary, and I will highlight preliminary results here, and we can look at Kling-Gupta efficiency, which is a simple evaluation metric where higher values are more skillful. And we aggregated all of these sites for all these 4 lead times for our 2 models in white and gray. And we can see, say, on April 1st, how is our SAC SMA model doing relative to the PCR model. And we can then break this out and look specifically at wet years or above average snow years or dry years or below average snow years. There's a lot of noise on these figures. We can look past most of it and just focus on the box plots themselves. And I think the most important takeaway here is that if we compare these wet years to the dry years, comparing similar lead times and models, we see that generally the models are more skillful during these snowier years and less skillful during these drier years. Within this, we do see patterns in which one model is oftentimes better than the other, depending on not only lead time or snow conditions, but also regional patterns, which I don't have time to go into here. And so there are some really important implications even from these preliminary results. We're able to show that both of these operational hydrologic models are less skillful during low snow years. Not only that, we also show in results not discussed here that skill is in fact degrading, at least regionally, particularly in the Pacific Northwest, through time. And so this does raise some concern for the long-term operational utility of these models, and sort of raises some questions about how they will continue to perform under lower snowpack in the future. And so this really feeds well into the second study, which I'm going to discuss with you today, which we're now going to zoom closer into California and Nevada, specifically the Sierra Nevada, where we're trying to test out this question. Does this trend that we think we're seeing in that first study continue as we move to the end of the 21st century and snowpack continues to decline? And if this is indeed true, what is the value of including supplemental observations in these forecasts as a way to mitigate skill loss? To evaluate this, we create, as I mentioned earlier, these synthetic water supply forecasts. So this is done exclusively in the VIC world, so the variable infiltration capacity model from the CalAdapt data set. And so we're using simulated predictor variables, SWE&P, and extracting the grid cells that are co-located with real observation stations, and then using these specific grid cells as more or less surrogates for future point observations. We can then train these predictor variables on simulated April through July runoff, similar to the NRCS method I mentioned earlier, and create, in this case, just a single April 1st forecast across many different GCMs for different time periods running all the way through the end of the 21st century, and then do this both for a low and high emissions scenario. And so if we do this on a basin by basin basis and look at the changes from the historical, that is the late 20th century to the late 21st century, and here we're just focusing on the high emission scenario, we see that we're projecting and simulating a water supply forecast skill loss of over 20%, and that this loss of skill is unevenly distributed and concentrated in these northern Sierra basins that are at a much lower elevation, whereas we see generally robust skill performance through the end of the 21st century, even under this high emissions scenario for these higher elevation southern Sierra basins. And this clearly is a response to the elevation mediation of decline in SWE. And so we can look more directly at that. So here on the y-axis, I'll take a moment to walk you through, is the change in a Nash-Sutcliffe efficiency. So larger declines represent larger loss in skill for this April 1st set of forecasts as a function of the change in April 1st snow water equivalent in millimeters. Each of these dots represents a single study basin, so there are 26 of them, where a small dot is the change from the historical baseline to the early 21st century, and the large dot is a change from the historical baseline to the late 21st century, and the line connects the two. And so we can see that as we lose more snow, we are simulating a loss in forecast skill. And generally, this translates into a loss of Nash.Cliff of about 0.15. And this is quite significant. And so this raises the question, of course, of how can we mitigate the loss of skill for these water supply forecasts, which Adrian mentioned are incredibly important in the Sierra Nevada for providing providing a sense of future water resources for the Central Valley in particular. And so right now we're in the process of evaluating the inclusion of additional simulated data. The first technique that we're evaluating is this remotely sensed snow water equivalent product. So one way to think of this is it's as if we're flying an airborne snow observatory measurement where we get a snapshot of snow water equivalent across the whole entire basin, and then provide that to our model and see if we can improve forecast skill. This would also be equivalent to the SNODAS product, if anyone is familiar with that. And then the second technique is the inclusion of soil moisture data. So looking at simulated soil moisture at existing precipitation stations to see if we can introduce some of this terrestrial water storage information that might be overlooked in the current model structure. So to summarize some of these take-home points, the first is that we believe that lower snowpack really does represent a significant threat to the scale of conventional water supply forecasts. And I think this is really well illustrated in this figure from Ben Livna, that as we move into a world of less snow, we're really losing this predictive power that snowpack has historically provided for spring runoff in these snow-dominated headwater basins. And in replacing this is going to be really challenging. But there are ways in which we can move forward to improve operational forecasts. Currently, I'm working with Andy Wood and Dagmar Llewellyn at the National Center of Atmospheric Research and the Bureau of Rec to implement the SUMA model developed by Martin Clark at a Huck 12 scale all across the Western US. We're currently evaluating this in the Upper Rio Grande for ensemble streamflow predictions. Other promising ways forward include an ensemble of multiple models, perhaps with the National Weather Service and the NRCS, which has historically been done, but also including new predictive variables such as soil moisture, but also perhaps some climate forecasts, or things like machine learning and other advanced statistical analyses. So with that, I'm happy to take any questions. Thanks so much for your attention.
Great, thanks, Josh. That was a great presentation and very interesting. I hadn't seen this before. So I know we only have a couple minutes left. We have had a couple questions come in for both you and Adrian. And so I will try and go back and forth between the different questions. I guess there were some for me too. And we'll use the remaining time for the questions. So one of the questions was, how, Adrian, is your work related to the GRACE mission?
Okay, I can make this really quick. GRACE and GPS see the same thing, but at completely different resolutions. GRACE is amazing for global coverage at sort of 300 kilometer scale and larger and monthly timing, and this is much smaller, higher resolution in both time and space. Good question, thank you.
Thanks, Adrian. One of the questions for me was actually looking at the soil moisture maps. There was a strong kind of difference between California and Nevada at the border, and asking if that was something that was really there or some product of the modeling. And I don't have a good answer for that. Dennis Ledemeyer, who runs this, I will follow up with him and see if I can dig deeper and understand what's going on. But it was a good question. I noticed it as well. Unfortunately, I just don't have an answer for that. And another question, Douglas, we had for you is, how do you account for the local elastic storage so you can remove that from the data? Sorry, Adrian.
Local elastic storage. So we invert for everything, and the local as, okay, how do you account for the local aquifer? That's, I think, the question. We take those stations out of the inversion, which still works because each station sees loads that are close and far. So it's really important here to separate the physics, and we do not do anything. We do not use data over an aquifer other than to go see what the aquifer is doing. Thank you. Good question.
I was muted. And then there was a question about the eddy forecast from my presentation. And the question was, over here, sorry, let me just read it. Why is the eddy forecast for the eastern border of the Southern California dry if this area was getting above average rain? And so the eddy forecast does not include precipitation. It looks at atmospheric drivers to calculate evapotranspiration. And so this is looking at temperature, humidity, solar radiation, and wind. And so when you combine those, that's an indication of how much evapotranspiration or the thirst for the atmosphere. And so precipitation doesn't actually play into it. And so that's why you see the difference between eddy and actually the precipitation anomalies. And then there are a couple of people, so I realize we're just over, and I apologize that we didn't get to all the questions. We're at the hour point. I just want to let everybody know that these presentations will be available on the YouTube channel. And then when you sign off, there's a very brief survey that is helpful for us just to know who is joining and how we can make these better. So thank you to our presenters, both Adrian and Josh. Very nice, very interesting presentations. I learned a lot. So thank you very much. And thank you all for joining us. Have a wonderful week. Thanks again.